ChemStars, it's Ms. McCauley, and we're going to be going over chapters 14 and 15 notes, page 9, and it's all about neutralization reactions. I know you've been anxiously waiting till we come back to BCA tables again, and here it is. So our objective is that we can write and balance simple equations for neutralization reactions. So when an acid mixes with a base, it's going to neutralize. It's like a type of double replacement reaction. So the products will always be water. So the acid, the H plus, is going to combine with the hydroxide, OH minus, and create water. And salt. Now, let's talk about what a salt is. Table salt, is sodium chloride. But if we're talking about a chemical salt, chemically, a salt is going to be either a group 1 or a group 2 cation. That's things like sodium, potassium, lithium in group 1. Or in group 2, that would be calcium, magnesium, strontium, plus an anion. It's usually going to be a halogen or a halide in group 17. That's chlorine, fluorine, bromine, iodine, or it could be a polyatomic anion. So the salt is going to be that combination of a group 1 or group 2 metal plus a halogen, halide, or maybe a polyatomic. So let's go through this example right here. So you can see if we have hydrochloric acid, that's the source of my hydrogen. And we have sodium hydroxide, that's the source of my hydroxide. The H and the OH go together. And when you put H and OH together, you get water. Just like we learned in our chemical reactions, we've got to then pair the other cation and anion together. So look at that. The chlorine was with hydrogen, now it's going to go with sodium. And look, we get sodium chloride, regular old table salt. And when dissolved in water, it will separate out and be NaCl. Okay, so how about this next one? We have sulfuric acid, H2SO4, plus potassium hydroxide, KOH. Now, on that previous one, it was all 1 to 1 to 1 to 1. But let's break these up into their parts here. So SO4 you have memorized, or you can look it up. SO4 is always a 2 minus, and H is a 1 plus. That's why the formula has 2 H's in it. Potassium is always a 1 plus, and hydroxide's a 1 minus. So you can see right here, we're going to get the hydrogen plus the hydroxide. They'll go together and make water. Look what is left over. We've got K and we've got SO4 2 minus. So that formula, to balance out the -2, it has to be K2SO4. That's a review from your chapter 8. Just make sure you go back and look over those things. Last step, go through and check, is it balanced? 2 potassiums, put a 2 in front to get 2 potassiums, 2 hydrogens. That's why it's helpful sometimes to keep water written as HOH. You can trace your hydrogens and you can track your hydroxides right there. Okay, so that is your general format. So, like we already said, a salt is any ionic compound formed from an acid-base reaction. Usually it's going to be a group 1 or group 2 cation with a halogen or a halide. So now our second objective, we can conduct a titration experiment in order to determine the concentration of an acid and base equation. So a titration, our goal is to find the equivalence point. Another way of saying that is when it's neutralized, where the moles of the acid and the moles of the base will be equal. That means the pH will be 7. In the lab, we'll do that experimentally, drop by drop by drop, using phenolphthalein. But theoretically, we're going to use BCA tables and some chapter 9 stoichiometry to figure that out. So here's our first example. How many moles of HCl are required to neutralize 0.50 moles of sodium hydroxide? Well, the first step is that we need to write our balanced chemical equation. So we have HCl plus NaOH. Oh, acid-base neutralization. The H and the OH are going to go together and form water, H2O. Leave it as HOH, it's fine. What's left over? Na and Cl. There's your salt. Water is a liquid. Sodium chloride, when dissolved in water, is aqueous. Okay, now classic BCA table. So we need to do BCA. Now, before the reaction starts, what do we know we have? Before you make brownies, do you have brownies? Nope. So before the reaction starts, do you have products? Nope. Those are always 0. Now, how many moles of HCl? We don't know that. This is what we're trying to solve for. Are required to neutralize 0.50 moles of sodium hydroxide. So we're starting right here. We're putting in 0.50 moles of sodium hydroxide. That's this right here. We're starting here. It's being neutralized. So we are exactly using them both up. So during the change, how much of the sodium hydroxide am I going to use? Good job. All of it. How much is left over at the end? Good. None of it. So I can't get this to disappear. Let's see. There we go. I'm struggling with the smartboard, guys. What else is new? None of it's left over. So we're going to treat this one as our limiting reactant. Okay, so like we like to do, box it in, put a star by it, label it, limiting reactant. Everything is based off of sodium hydroxide. All right, they want to know exactly how much do we need to neutralize. That means they will be equal to each other. So we do not want any leftovers. So afterwards, we don't want any leftover HCl. Now during the change, look at the mole ratio. It's 1 to 1. What's my moles of limiting reactant? 0.5. So if during my change I've used up 0.5 times 1 over 1, how much have I started with? The same number. Good. So before the reaction starts, I must have had 0.50 moles of the acid. That's it. You've answered the question. That was pretty easy. It was straightforward 1 to 1 to 1. Did they ask me anything about these products? Nope. So I'm going to skip that for now. Now let's look at number 2. What if instead we still have our 0.5 moles of sodium hydroxide, but what if we had the H2SO4? Well, when we look at our equation, we have H2SO4 plus sodium hydroxide, H and OH, that gives us our water. Sulfate, like we said at the top of the page, sulfate's at 2 minus. So it's going to form Na2SO4. Go through, balance it just like you did in chapter 8, and you're going to see my mole ratio won't be 1 to 1 to 1. It's going to start out the same though. No products before the reaction starts. We have 0.5 moles of sodium hydroxide. We want to neutralize it, use it all up. So I'm going to use up all 5. None is left over. This is what we're going to call our limiting reactant. So the sodium hydroxide, put a star by it, outline it. This is my limiting reactant. We are exactly neutralizing. So how much acid is left over? None. Now here's the little bit trickier part. My moles limiting reactant goes out front. Now look at my mole ratio here. The unknown, the column that I'm in, over the known limiting reactant. So on this section right here during the change, I'm not using up 0.5. I'm using up 0.5 times 1 over 2. So what is 0.5 times 1 over 2? What's half of a half? You can use a calculator if you're not sure. Good, you got it. 0.25 moles of acid. Remember, that's going to be moles of my H2SO4. Are you surprised? I hope not, because it's the exact same setup, but the only thing that is different is this is a diprotic acid. It means there's 2 protons. So it kind of makes sense. For every 1 molecule of this acid, it can give off 2 hydrogens to help neutralize that hydroxide. So you need half as much. Okay, I want to get you started on this last one. I want you to pause the video and then come back after you've gotten our balanced chemical equation. I want you to do BCA, put in your zeros, figure out your limiting reactant, and then figure out how much acid you need to neutralize it. Okay, so pause the video and come back. Thank you, ChemStars, who actually paused the video. Good job. So before the reaction starts, no products, and they're telling me we have exactly 0.023 moles of H3PO4. So up here we have an acid with 1 proton. Here we have an acid with 2 protons. Now this time we have an acid with 3 protons. Okay, so let's go through and see what's going on here. So I want to use up all of the acid. I'm titrating it. I'm neutralizing it. This is my limiting reactant. So everything this time is going to be based off of the acid. So here is my limiting reactant. All right, now here is where we really do the real stoichiometry work. How much of the magnesium hydroxide can we neutralize? The same number, the moles of my limiting reactant times the mole ratio, the unknown column that we're in, over the known thing that we're searching for. So we want them to exactly neutralize. So at the end, there's going to be no left over. During the change, I'm using up 0.023 moles times 3/2. How much must I start with then? It's okay. Use a calculator. Take out your handy dandy calculator of science. Take your 0.023 times 3 divided by 2. And you should get 0.0345. And that's going to be how many moles of the base that you can neutralize. It's not exactly a third because look, even though this has 3 protons, this one has 2 of the hydroxides. Okay, ChemStars, that is how you use BCA tables to solve acid-base neutralization problems. Let's just look at the next page real quick. You're going to do more of this in class, so it's going to go through and talk you through exactly what the titration is, the point of neutralization, and just look at how quickly an acidic solution can go to a basic solution. Right at that equivalence point is where we're going to try and stop it when we get to the lab. Very, very similar. We're going to bring in chapter 12 stuff right here. So we're going to go back to our chapter 12, and we're going to use that to find our number of moles. So we have a molarity. We're going to have a volume. You know what's going to happen next. We're going to find our number of moles and plug that into our BCA table problems. Okay? So we're going to be taking HCl plus sodium hydroxide. Do all that stuff, and then you're going to figure out your number of moles. We'll do this together in class, but if you want to pause the video and get some of this written down, you can kind of get that ahead of time here. Okay, so we will go over this in class, but the last step is using our chapter 12 equations. Make sure you are only putting moles in. If you have grams, convert it back to moles. If you have milliliters, it's got to be converted to liters. That's how you'll get your moles. Like we did on the previous page, you want them to be exactly 0 to exactly balance. You'll use your mole ratio. You know the number of moles you start with. And if we know number of moles, we can figure out concentration by doing M equals N over L. Just make sure only moles for N and only liters for L. So if they told you use some number of milliliters, make sure you convert it to liters. Okay, we'll go over page 11 and page 12 more closely in class. Same stuff, we're splitting all of our chapters together now. All right, ChemStars, I'll see you next time. Bye.